Welcome back. In our last lecture, we discussed the PUL decomposition, which is true for every invertible matrix. And we could not do any example, and we promised to do an example. So I will start with an example of PLU decomposition in this lecture. Let me start by sharing the lectures. So I'm sharing the slides, and I hope you can all see the slides. So PLU decomposition, let's quickly review. Whenever we are given a system of linear equations, Ax equal to B, if we knew in advance the row interchanges that would be needed to solve it by GEM, then we could arrange the original equations in an order that would ensure that no row operations are required. Okay, so this is just a theoretical discussion to show that PUL decomposition holds. PLU decomposition holds. It's only theoretical. So, given any system of linear equations, either you will have to apply row interchange operations or you will not have to apply. If you don't have to apply, then you have an LU decomposition anyway. But if you have to apply, then you could perform those operations already before applying the starting the Gaussian elimination. So what it tells you is that for every invertible A, there is a P, which is the permutation matrix, with the property that PAX equal to PB does not require row interchanges. And therefore, this PA will admit a factorization as LU, where L is lower triangular and U is upper triangular. And then by taking the inverse of P to the other side, we get the PLU decomposition, which is the decomposition of your matrix A. It's a factorization of your matrix A as a product of a permutation matrix P prime, a lower triangular matrix L, and an upper triangular matrix M, and in that order. That's what we have been able to compute. Now we need to go and do some examples. So consider this particular matrix. Now the first pivot already A11 is 0, so we will not be able to we will not be able to start the Gaussian elimination. So a pivot has to be partial pivoting has to be done, or we will have to interchange the E1 and E2. So after doing interchanging, we will then apply E3 plus E1. So 1 will have to be eliminated from E3 and also from E1. So we will do E3 plus E1 instead of E3 and E4 minus E1 instead of E4 to get the matrix, which is going to be a matrix where the first column does not have x1 anymore, or after the first diagonal entry, the first column has only zeros. Now this second pivot is again 0, and therefore we have to again do the interchange. So the interchange now will have to be between the second row and the fourth row. So these two have to be interchanged, and once you do that, then you will apply E4 plus E3 to E4 to finally get this particular matrix, because once you have applied this change of rows, you will have 1 here and zeros below, but you will have, instead of this -1, you will get 1, and this 1 is there. So this the E4 and E3, the ones, the variable x3 has to be eliminated from the equation E4, and so we will have to interchange, we will have to apply this row operation for that. Okay, so this is the final upper triangular matrix that we are going to get, which is upper triangular now. So this upper triangular matrix is obtained, but there is a permutation matrix which we have done. So the permutation matrix which is associated to row interchanges, there were two such row interchanges. The E1 was switched with E2 and E2 was then switched with E4. So we had E1 switched with E2 and E2 was switched with E4. So this is given by this particular permutation matrix. What it does, is that, you know, you will see where E1 goes at the end. E1 is going to the place of E2 in the first row interchange. Now it is, while I'm writing E2, but it's actually the original E1. So that has gone to E4. So when you are looking at these two row interchanges one after the other, E1 has gone to E4. And therefore, instead of having the first non-zero entry equal to 1, we are putting it as the fourth non-zero entry equal to 1. What happens to E2? E2 in the first row interchange has gone to E1, and now it has gone to E1, so the original E2 does not change. Therefore, E2 has gone to E1. There is only one non-zero entry in the second column, and that's in the first place because E2 has gone to E1. E3 has not changed at all. You know, the changes are happening for E1, E2 and E4. E3 has not changed, so the E3 non-zero entry remains as it is in the diagonal. And finally, E4 is not changed by the first row interchange, but it is changed by the second row interchange and it goes to the second place. Therefore, you have 1 in the second place. So this is the understanding to get this particular permutation matrix P, but you may check. You may put this matrix P and you may put a 4 by 4 matrix and see what happens when you multiply by capital P on the left of A and see how the rows are interchanged. So what we then have is PA. So after having, so you know, we have our original A which was given to you. This is the A, and we now notice that there is this permutation matrix which has to be multiplied to it by. So this is our capital PA. On this matrix, we can perform the Gaussian elimination. The operations are the same as before. Operations will not change. These are the operations. You take E1, E2 minus E1 goes to E2, E3 plus E1 goes to E3, then E4 plus E3 goes to E4. And so the non-zero multipliers for PA are these. And then we get the corresponding LU decomposition. This is the LU decomposition for PA. And then the decomposition or the factorization for capital A is this. So this is the inverse of the earlier matrix. So in the first column, we had 1 at the bottom. Now in the first row, we have 1 at the end. For a permutation matrix, the inverse is also given by taking the transpose. So we are simply taking the transpose. So this is the decomposition of our matrix A as a product of a permutation matrix, a lower triangular matrix, and an upper triangular matrix. Solving this system when you have a lower triangular matrix and an upper triangular matrix is very easy, because you will first solve for the lower triangular matrix into some vector y. Okay, so when you had Lux equal to B, we solved for Ly equal to B, where y was ux. So after solving Ly equal to B, we then solved for ux equal to y by the backward substitution. The Ly equal to B was the forward substitution, and ux equal to y was solved by backward substitution. Now we have one more matrix. So we have this PLU x equal to B. So we look at LUX as Z, and we are solving for PZ equal to B. But P is just a permutation matrix. It's going to only permute. So the Z can be easily obtained by permuting the B entries. And so you would have LU equal to the permuted B. So LUX equal to permuted B. And you have to now solve for that. So that permuted B is your Z. Okay, so we have solved for PZ equal to B is solved. And now we have to solve for LUX equal to Z. That is same thing as looking at Ly equal to Z, where Y is UX. So that Y can be solved by forward substitution, and then you solve for X in UX equal to Y by backward substitution. So, all right. So what happens is that, of course, it is of interest to write a matrix A as PLU. We would still want to know the cases where we don't have to deal with the permutation matrices, because it brings some baggage with it. So we would like to understand the systems where we don't have to do that. And those are some of the matrices that we are now going to look at. So there are these systems of matrices called diagonally dominant matrices. So these are the two particular classes of matrices for which we are going to study how the Gaussian elimination can be performed effectively without row interchanges. So the effectively is something which will be clear towards the end of the lecture. But at least without row interchanges, we can apply the Gaussian elimination without changing the row. No interchanges of row. So what is a diagonally dominant matrix? An n by n matrix is said to be diagonally dominant if you have. So what you do is that you take a row, ith row, and you put moduli for each of the entries. So you, instead of taking the entries ai, you take the absolute values of all these entries. Then the sum of the non-diagonal entries in the moduli should be less than or equal to the modulus of the diagonal entry. The diagonal entry has to be the biggest, not just biggest, it has to be bigger than all others being summed after taking the modulus. So it has to be really very big. That is what is called a diagonally dominant matrix. And if this inequality is strict, then we call the matrix to be strictly diagonally dominant. It's a very strong condition, and therefore such a matrix should have some nice properties. What are those properties? First of all, a strongly diagonally dominant matrix is invertible. Secondly, in this case, the Gaussian elimination method can be performed on any linear system of the form Ax equal to b, which is to say that for any b, we can perform the Gaussian elimination to obtain its unique solution without row interchanges. We do not need the row interchanges. And now I come to the effective part. Furthermore, these computations will be stable with respect to the round of errors. The round of errors do not disturb the diagonally dominant matrices much. This is the effect of having the strict diagonally, a strongly diagonally dominant matrix or a strictly diagonally dominant matrix. So this is all the three statements that I have written above. This is a very, very serious theorem, which we will of course not prove in our course, but what it tells us is that the strongly dominant matrices or the strictly dominant matrices, they are very useful. We should study them. We will look at matrices which are strongly dominant, strongly diagonally dominant, and then we will apply the Gaussian elimination method to them. This is what we do about these diagonally dominant. And the second class of matrices is the positive definite matrices. So a matrix A is called positive definite if first of all it is symmetric and it has this somewhat strange property, which is that X transpose AX is positive for every non-zero X. So let's look at it again. Your A is an n by n matrix. You multiply on the right of A by a column matrix. X is a vector, so it's a column matrix. So you have n by n into n by 1. So you are going to get ultimately the product will be a column. Okay, and to this whole thing on the left you are multiplying by a row, X transpose. So you are multiplying by a row to an n by n matrix to a column, which will finally be a row multiplied to a column. And so this is 1 by n, this is n by 1. The product will be a 1 by 1 matrix. And we are looking at real numbers. So this is a 1 by 1 matrix having a real entry. So when I say that this X transpose AX is positive, I mean to say that the corresponding entry is positive. Okay, but it's again a very strange condition and it has something to do with the theory of bilinear form. But right now, let's go into that. Let's not go into that. We will look at suppose this A is given by the entries Aij, and your column vector is given by the transpose of this row. So this x1, x2, xn keep written horizontally is the row, its transpose will be the column vector we are looking at. Then this computation x transpose ax is this particular one. I going from 1 to n, j going from 1 to n, aij, xi, xj. This is what it looks like. This entry has to be bigger than 0, strictly bigger than 0 for every non-zero x. That's when we call the matrix to be positive definite. And also, of course, it has to be symmetric. The symmetric property is sometimes not assumed. If you are looking at some other source, it is likely that the symmetric property will not be assumed, but we are going to ask for that. So our positive definite matrix is one which is symmetric, and moreover it has that particular property. So the matrix then, so let's do an example. We have this matrix 2 minus 1 0 minus 1 2 minus 1 and 0 minus 1 2. We want to know whether this is a positive definite matrix, and the statement is that yes, it is a positive definite matrix. So we need to compute that x transpose ax and see whether it is bigger than 0 for every non-zero x. But to do that, before that, we begin with us observing that our matrix is indeed a symmetric matrix. So you can now go to the next condition. If it was not a symmetric matrix, it will not be positive definite by our definition. So we need to make this observation and note it down that it's a symmetric matrix. And now I compute this. I told you, I gave you the formula for this. It is summation aij xi xj, and xi xj and xj xi. Their coefficients are brought together. So there is a small typo here. This should have been a minus sign here between 2x2 square and 2x2 x3. But in the next part, it will have been taken care of. So we can write this x transpose ax as summation of these four squares. x1 square plus x1 minus x2 whole square plus x2 minus x3 whole square plus x3 square. Now, if your matrix, if your column vector is not equal to 0, 0, 0, then this thing is definitely positive. This cannot be 0. It's a summation of squares. So it cannot be a negative quantity. It can be 0. If it is 0, your x1 will have to be 0, x3 will have to be 0, x1 minus x2 will have to be 0, which means that x2 is also 0. And x2 minus x3 is 0. This is an additional condition anyway, which is also giving you that x2 is 0. So if your x transpose ax is 0, then x has to be the 0 vector. But our vector is not 0 vector. Therefore, this product x transpose x has to be a positive real number, and which means that our matrix A is a positive definite matrix. So already for 3 by 3 matrices, we had to do some non-trivial work to check that our matrices are, our matrix is a positive definite matrix. So it is clear that using the definition to determine whether a matrix is positive definite or not is going to be a bit difficult. Fortunately, there are some other criteria which are quite easily verified. They can be easily verified, and we will see them later, because the set of positive definite matrices is a very, very important class of matrices. So here are some necessary conditions, which necessary means that if your matrix is positive definite, then something should follow. So what are those things? First of all, it has to be an invertible matrix. Every positive definite matrix is invertible. Moreover, its diagonal entry has to be positive. If you have a matrix, if some matrix is given to you, and if it is asked to determine whether it is positive definite or not, And if you notice that some diagonal entry is negative, or if some diagonal entry is 0, then you know that the matrix cannot be positive definite. There are some more important conditions. The aij square, whenever you are looking at any I and j which are not same, look at that square again, the one that I had talked about in the last lecture while discussing the permutation matrices. So you have ith row, jth row, ith column, jth column. This is a square and it has 4 corners. There are, what are the entries? The entries are AII, AIJ, AJI, but AJI is AIJ because it's a symmetric matrix, and AJJ. Then the product of the diagonal entries is bigger than the product of the off diagonal entries of that particular square. And finally, the maximum of mod AKJ, where you are looking at all the Ks and all the Js, this is less than or equal to maximum of mod AII. So the maximum taken over all the entries of the moduli of the entries is achieved on the diagonal entries. That is what it means. So these are some very interesting properties. However, these are not sufficient for a matrix A to be positive definite. So we will now look at a necessary and sufficient condition for a matrix to be positive definite. Before that, we will need to introduce one small concept. A leading principal submatrix of the given matrix is this particular matrix. You have your n by n matrix. What you do is that you take first k rows, take first k columns. That gives you a k by k submatrix. Okay, it's the top left k by k submatrix, which is called leading principal submatrix. Now the condition is coming, a matrix A is positive definite if and only if each leading principal submatrix has positive determinant. A very easy thing to verify. You don't have to look at x transpose AX and then compute it and write it as sum of squares. That does not have to be done. You have to just form these n leading principal submatrices and compute their determinants. They all have to be positive. That's the only thing you need. For instance, the matrix that we had looked at was this: 2, -1, 0, -1, 2, -1, and 0, -1, 2. Our first leading principal submatrix of order 1 is just 2, and the next one will be 2, -1, -1, 2. So A1 is 2, A2 is 2, -1, -1, 2. What are the determinants? For the A1 it is just 2, and determinant of A2 is 3. And also the determinant of the whole matrix is 4. So all are positive and therefore our matrix is positive definite. This is a much simpler criterion than looking at the x transpose AX, than working with the definition. Okay. So now we will record some results which imply how our positive definite matrices are interesting. So for instance, whenever you have a matrix to be positive definite, then the Gaussian elimination method can be applied to any system without interchanging rows with all pivot elements positive. In fact, this is if and only if condition, provided that your matrix is symmetric. So if you start with a symmetric matrix and if the Gaussian elimination can be applied to Ax equal to B without row changes, and the pivot elements remain positive in all these subsequent steps, then the matrix has to be positive definite. This is the parallel of the condition for strongly dominant matrices. The strongly dominant matrix also had this property, although it was not equal if and only, but whenever you had strongly dominance condition, and then we have that the Gaussian elimination can be applied without row interchanging. There was no condition on the pivots being positive. Moreover, in this case also, the computations are stable with respect to the growth of round off errors. So this is why the strongly dominant matrices and the positive definite matrices are of our interest. Moreover, there are some very interesting factorizations for the positive definite matrices. What are those factorizations? A matrix is positive definite. Now we don't have to put the symmetric property in the definition. In the previous part, we had to say a symmetric matrix is positive definite. So the symmetric part was being assumed. After having assumed symmetric part, the next two conditions are equivalent. Okay, but here we don't have to do it, and you will see immediately because LD L transpose is already symmetric. D is diagonal, and then if you take the transpose of LD L transpose, you will get L D transpose L transpose. You know that if you have A B C product and you take the transpose, you are going to get C transpose B transpose A transpose. So you are going to get transposes, but the order is going to be switched. So here this matrix A is positive definite if and only if you have LD L transpose. Moreover, L is lower triangular whose ones have diagonal, whose diagonal entries are all 1, and D is a diagonal matrix with positive diagonal entries. Now once you have D with positive diagonal entries, every positive real number is a square. You can write it as a square of some another positive number. So each diagonal entry is a square, and therefore you can write this capital D, the diagonal matrix, as product of two diagonal matrices whose diagonal entries are the square. So in fact we have written capital D as a square of a diagonal matrix. Okay, and that square, the left hand side square can be put inside L, and the right hand side square can be put inside D transpose, L transpose, and so we get a matrix is positive definite if and only if you get that A is L transpose, where L is a lower triangular matrix. Now we have no condition on the diagonal entries, because whatever the diagonal entries are, they are going to be squared. So even if they were negative, the squares would be positive, and so we don't have to worry about this. This is a very interesting factorization. In fact, this is something I had told you some time back in the last lecture, I believe, that when you have a factorization of some matrix A as LU, where the diagonal entries are same, then it is called a Cholesky factorization. It's a very important factorization. It is time saving factorization, and once you have this factorization, you can apply and solve the systems quite easily. So this is the Cholesky factorization, and what we have is that a positive definite matrix has Cholesky factorization, where the upper triangular matrix is simply the transpose of L. Note that just being positive definite is not enough. It's not even necessary to admit a Cholesky factorization. You just want L into U, where L is lower triangular, U is upper triangular, and of course, the matrix 0 admits the Cholesky factorization, for instance, because 0 is 0 into 0. 0 matrix is lower triangular and 0 matrix is also upper triangular. So admitting Cholesky factorization is not equivalent to positive definiteness, but whenever you have it to be positive definite, you will get a Cholesky factorization. So let's now, to end our lecture, let's try to compute the Cholesky factorization of this particular positive definite matrix. Okay, so we have written it as the lower triangular matrix into the transpose of that lower triangular matrix, and we just compute the squares on the right. So compute the products on the right. So let me just explain it to you. First of all, we are, we have a lower triangular matrix L, and you are multiplying by L transpose, so you are going to get a symmetric matrix. Therefore, to solve, we look at only the lower triangular part. Okay, so L11 square is equal to 4. That tells you that L11 is 2. The entry below that is L11, L21. This is -1. You have solved for L11, so you can solve for L21. Similarly, L11, L31 is 1. That allows you to solve for L31. So we have solved for the L11, L21 and L31. Next, we look at the second diagonal entry, L21 square plus L22 square. Out of them, L21 square is already computed, and you have it equal to 4.25. It's a positive definite matrix. Therefore, L22 square is also a positive quantity, and there you can then take the square root to get L22. Once you have computed L22, put it here and you will be able to compute L32. L21 is computed and L31 is computed already in the first column. L22 is computed and then you use it to compute L32, and in the end you will look at this particular last entry, the 3/3 entry, and compute L33. This is how the whole computation can be done. I will just write it here. 4 equal to L11 square, so L11 is 2, minus 1 equal to L11 L21, so L21 is minus 0.5, 1 is L11 into L31, so L31 is half, 0.5, L22 is 2, L32 is 1.5, and finally L33 is 1. Now we can write it back as L into L transpose. And this is where we are going to stop in today's lecture. We could not complete an example in our previous lecture, but this time I did that example, and even for the Cholesky factorization, we have been able to complete an example. We will begin our next lecture with some more interesting properties and concepts in linear algebra. See you in your next lecture. Thank you.